All right, let's get started. Welcome everybody to Proving Ground. First, I want to thank our sponsors. We have Verisprite, Providi, I actually don't know how to pronounce that, Tenable, Amazon, Source of Knowledge, and all of them are located here in the Chill Out area, so definitely check out their booths. Please keep your phones on silent and be respectful of the speaker. And also, please fill out the forms that are online for feedback of the actual talk. This is Keith Krause. He's an associate principal at Accenture, and he's going to be talking on scalability, not as simple as it SIEMs. Welcome him.
Thank you. Got to start with a pun. All right, so hi everyone. I'm Keith Krause. I'm an associate principal engineer at Accenture's security lab. And just to give you a little bit of background, Accenture Labs is the most forward-looking part of Accenture. We're looking at things 3 to 5 years out that are going to cause disruption in an industry. And so my talk today is focused on some of the work that I've been doing at our security lab in the Washington, D.C. area. So security data science is hard. Currently, it's not being done well at the scale and the volume of data and alerts that analysts are receiving every day. So enterprises are constantly changing, with more devices being added at a faster pace than ever before. There's more bring-your-own-device programs, and new technologies are constantly being added into enterprise IT. So more devices, more people, distributed workforces, it's creating a really difficult security problem of ensuring that people aren't using your network maliciously. And it's easy to see that we're struggling in a day and age when privacy and security is on everyone's minds. So the Ponemon Institute put out a report recently that says for most financial services institutions, it takes an average of 98 days to detect an advanced persistent threat or a zero-day malware. That's 98 days where someone malicious could be stealing your identity or stealing your financial information. And on the other hand, this takes up to 7 months for retailers. So Wired magazine put out an article recently about how the CIA handles cybersecurity different than most enterprises. So in addition to just trying to encrypt everything and just protect the perimeter, the CIA is starting to develop systems that can kind of prioritize events and problems and create intelligent ways to respond to threats. So they said that the challenge that lies in this is efficiently scaling these technologies for practical deployment and making them reliable for large networks. So my work has been focused on building a platform that can act as the base layer for such systems. So enterprise security has a data problem. In a modern Fortune 500 enterprise, 1.5 terabytes of data consisting of 250 million events daily is the norm, and they are not equipped to handle it. So for most enterprises, the starting point to tackling this problem is SIEM, but SIEM is only a starting point. Endless time and money have been spent by enterprises in refining their SIEM solutions, but SIEMs weren't originally designed to handle the amount of data that we're producing today. And so this shows mostly through 2 main areas, which is the storage retention and the computational power of SIEMs. So most SIEMs are only able to have a 30-day window of data available online. And then data beyond this 30-day window typically has to be archived. So this archived data is typically stored inefficiently, where you're either sacrificing storage space or speed in order to kind of load it back into the environment to then query it. And then additionally, working on only a 30-day window vastly reduces your effectiveness in kind of detecting and reacting to these advanced persistent threats. So in addition to this, asking simple questions such as, which machines did I see this executable on in the past few months, shouldn't take hours or even days to run. And asking the wrong question or just mistyping something shouldn't take hours to then return the wrong results. So what I'm trying to say is the modern SIEM, it's a great pane of glass to see what's happening now, but it's very ineffective about answering more advanced questions. So enterprises need to move beyond these basic questions and rules and start building models and analytics to detect these more advanced threats. And in order to answer these complex and demanding questions and start building these models, a big data-driven solution is needed. This solution needs to enable both analytics and models at scale that can keep up with modern enterprises' data volume and velocity. When an indicator is found, an analyst needs the ability to immediately pivot on data, or as we say, pull the thread, to kind of follow a threat from its infancy all the way until its exfiltration. So, which brings me to my research hypothesis. Cybersecurity has a big data problem. The volume and velocity of data from devices requires a new approach that combines all data sources to allow for more intelligent and advanced cybersecurity hunting through analytics and exploration at scale across enterprise data. And along with this, open source big data technologies reduce cost and act as the building blocks of a scalable platform with the speed necessary for enterprises to overcome these challenges. Combined with long-term historical data, enterprises will be able to reduce noise and empower analysts to effectively detect threats. So before I dive into a big data architecture, I want to make a point very clear. I'm not saying to replace or abandon your SIEM. CISOs would not be very happy if we told them to just get rid of the software that they've invested thousands of hours and millions of dollars into. So this time and money that's been invested by enterprises into fine-tuning their SIEMs makes them great data sources, but siloed data sources. If you're an analyst trying to hunt or follow the thread of a threat, you're going to need additional data sources, such as like your vulnerability scanner to see if a server had any known vulnerabilities, or your threat feed to see if it accessed any kind of known malicious entities. It's a huge waste of time for analysts to kind of be jumping between SIEM to their vulnerability scanner, back to SIEM, to their threat feed, back to SIEM. What they need is a single solution that kind of gives them a clear picture. So diving into the architecture now, first part, Kafka, it's an ingestion engine. And by using Kafka, we can ingest a number of different data sources, and it allows us to combine these diverse and typically isolated data sources and store them into a unified place in HDFS. So using HDFS as a data lake is common in the big data space, but for cybersecurity, what it does is it offers us a way to break down these data silos and bring all these diverse data sources together and provide a complete picture for a security analyst. So in order for the security analysts to actually ask questions and kind of hunt things, they need a query layer. And what this architecture gives you is Spark. So Spark provides an easy way for analysts to very rapidly ask questions using very industry-known languages such as SQL or Python. So Kafka, HDFS, Parquet, and Spark, they're all open source Apache projects. So there's no licensing fees, there's huge community support for them, and there's typically rapid updates that generally yield good performance increases and new useful features. And so typically analysts would interact with a platform like this through an interface such as a Jupyter notebook or a tool using Graphistry, but I'm not going to dive into them on this talk. All right, so Kafka is a distributed publish-subscribe message queue that's extremely fast, scalable, and durable. So at a lower level, Kafka is composed of producers, consumers, and brokers. So producers are what send messages to the Kafka cluster. Consumers consume messages from the Kafka cluster. Producers and consumers write and read messages from different sources of data called topics. And brokers are internal to the Kafka cluster and kind of manage these topics internally. So brokers receive messages from the producers and then send the messages to consumers. So why Kafka is important also is that messages are ordered as they are sent. So as you get event data in, it feeds event data out in the same order, so you don't end up with things out of order. And then messages are delivered with at least once reliability and allow for replication, so it protects you against the case of any kind of failure. So I touched on it in the previous slide, but Kafka gives us the ability to ingest a multitude of diverse data sources, such as SIEM, your vulnerability scanner, your threat feed, or any other kind of data source that you want, and then combine it into a centralized location. But most importantly, it does this at the speed and reliability necessary for enterprises. So in a large enterprise, the SIEM alone can easily generate more than 1 billion events per day at peak volume. But Kafka can easily handle this. So LinkedIn actually recently ran extensive benchmarks on Kafka, and the results showed that on very commodity level hardware, Kafka is lightweight enough where the limiting factor is almost always disk I/O or network I/O, and that Kafka can scale to the extremes, where at LinkedIn they're using a Kafka cluster in production, and they handle 800 billion messages a day with over 175 terabytes of data moving through it. So on the storage side, HDFS is very common in the big data space. HDFS is the Hadoop distributed file system. And so it's a distributed file system that provides a very scalable and reliable. So it provides a very scalable and reliable data storage using commodity hardware. And it's the data storage backbone of nearly all big data technologies, and all big data technologies integrate with it. So because of its integration with big data technologies, it allows us to exploit certain things that typical distributed processes don't allow, which is like data locality, so that you're minimizing your network transfer to kind of squeeze as much performance possible out of a distributed system. So on HDFS, any file format can be used, and typically you see things like CSV or JSON being used. And then on the big data side, there's other things like sequence files, but there's a new file format out called Parquet that's shown very promising results, especially for security data. So Parquet is a columnar storage format that was built from the ground up to support very efficient compression and encoding schemes. And so what this means is that the data is stored much more efficiently and can be read much faster. So in a typical table, you have your row-based storage where data is stored A1, B1, C1, A2, B2, C2, et cetera. And so the problem with this is A1, B1, and C1 typically will be very different data, so you can't really encode it intelligently, and that hurts your compression. Since Parquet is a columnar storage format, data is stored A1, A2, A3, A4, A5, B1, B2, et cetera. And so since the data it's by column, typically if you're storing an IP address, those IP addresses are going to be similar. So it makes it much easier to encode and compress this. So Allstate, the insurance company, recently did benchmarks on a couple different data sets. So they had one data set with 3 columns, and they found that counting messages using Parquet was about 10 times faster than using CSV, and the file size was actually 5.5 times smaller. They ran the same benchmark against a data set with 103 columns, and counting messages was 25 times faster, and the file size was about 41 times smaller. So at the Accenture lab, I actually ran a similar benchmark, except using SIEM data. And so in a data set with more than 450 columns, I found that counting messages was about 30 times faster using Parquet than CSV, and the file size was about 45 times smaller. So while performance is great, another feature that Parquet gives you, because it's a columnar store, you can actually add columns to existing data stores. So say you have your threat feed, and then, for example, they kind of add some new metadata. You can actually just kind of add the columns as you go, and it maintains compatibility with your older data. So Spark is a general cluster computing framework that's designed around providing in-memory computations to accelerate performance. So Spark follows a master worker model where a master node kind of issues tasks to worker nodes, and then the worker nodes deliver the results back to the master node. And so under the hood, Spark uses a lazy evaluation model, and it allows it to kind of optimize things like data locality and predicate pushdown, so just squeezing more performance out of the resources that you have. So within the context of a cyber big data platform, Spark would be used to ask questions on your data. So as you can kind of see in the slide, Spark has very easy programming interfaces that are very well industry known. So you see an example Python query, or you can do the same query in Spark, where basically you can put this in front of any security analyst, and with minimal uptime, they can kind of get running on it. And Spark also supports programming in Scala and Java, and it gives a small amount of advanced features and a very small performance bump. So in addition to kind of just basic features like filtering, grouping, and transforming data, Spark kind of gives us a platform to build scalable models in analytics. And Spark also has a few libraries. So it has the Spark machine learning library called Spark MLlib, which is a full and somewhat mature machine learning library. They have a stream processing library called Spark Streaming, and they have a graph processing library called Spark GraphX. So using this architecture, I actually ran a benchmark. So following the Kafka, HDFS, Parquet, and Spark architecture that I previously outlined, a day of data and a week of data was tested. So for the big data solution, we used a 10-node cluster that was under $50,000 in hardware. Then we tested this against a production SIEM instance that was being used at a Fortune 500 enterprise. So the data set consisted of more than 450 columns and approximately 250 million events per day. For the big data solution, the data was stored in Parquet on HDFS, and all the queries were run using Spark version 1.6. And the big data solution considered the query finished when the data was returned to the master and converted into a pandas data frame. And for those of you that aren't familiar, a pandas data frame is just a data structure within a very commonly used Python data science library. So here are some of the results from the benchmark. And as you can see, the big data solution is magnitudes faster than SIEM, even when loading all 450 columns, when SIEM is only typically loading 10 or so. And the SIEM solution was actually unable to finish running a query for a week of data in most cases. And in talking with the client team, they said that basically they would have had to split the query into multiple time units or allocate more resources to run it, and they just couldn't do that because it's a production SIEM. They did estimate that the queries would take more than 20 hours to complete each. And I just want to make another note. A lot of the time in the big data solution speeds was actually spent pulling the data into memory on that master node and converting it into a pandas data frame. If we just decided to write the results out in parallel to something like a CSV or even a Parquet file, the results would be even lower. And so this is important because looking past a day or a week of data, this solution easily scales into months. At our lab, we've easily queried more than 6 months of data at a time and been able to run queries in under an hour easily. And since this was done on Spark 1.6, Spark 2.0 was actually just released. And they've shown a magnitude of performance increase, so we can expect these times to just improve. So with the new speed and flexibility offered by a big data solution, it allows new use cases where SIEM struggles. And most of these use cases kind of break out of this 30-day window and the ability to look at even 12-plus months of data. So for example, full text search over 12 months of data. So you can proactively search for an EXE or a username over a year of data. Compliance request. This is something that the client team specifically told us, that finding all failed logins for a user over 3 months or 6 months or 12 months of data is just very difficult in current SIEM solutions. Then we can get into some more advanced things, like you can baseline log flows. And so you can detect when a device is emitting more or less log than usual. And what this allows you to do is kind of find, oh, is there a misconfiguration? Is this device been brought off the network or something? And what it also kind of allows you to do is baseline what the normal events that you see from a device are. So if we normally just see a ton of session open, session closed from a firewall, and then all of a sudden we're seeing something different, why are we seeing something different? Has something malicious happened? And most importantly, what this will allow you to do is accelerate your new SIEM rules and filters. So what this will allow you to do is proactively test a new filter or rule that you're looking to put in place in your SIEM. And it allows you to run this over 12 months of data very quickly. So it gives you this kind of rapid, interactive prototyping environment that SIEM currently doesn't give you. That's my talk. Any questions?
Yeah, so you mentioned earlier in the talk that you shouldn't throw away your SIEM
Yes.
to institute something like this. What if you didn't have a SIEM already? Should that person forego SIEM and just do big data? Should you do SIEM first and big data, do them at the same time?
So it honestly depends on your environment. So current SIEMs, what they do really well is they do correlation, they do some normalization, and at this state, we're not trying to recreate that. So why try to recreate something that already exists in most of these big enterprises? So just use that correlation, use that normalization that they've already done, and put it in. If you don't have a SIEM, that's your prerogative, whether you want to implement a SIEM or whether you kind of want to build that correlation and normalization into a big data solution. One thing I will say is there's a project coming out from Hortonworks and Cisco called Apache Metron, which is a continuation of Cisco's OpenSOC, which is kind of a SIEM built on top of some of these big data technologies. And it's showing a lot of promise so far.
You mentioned Kafka, and just like to dig into the problem I always hear with it, and you mentioned it was it's deliver at least once.
Yes.
Right? How do you see people dealing with more than once? I got an event.
So
I got it again.
Yes, that is something that you will have to kind of handle within your processing pipeline, unfortunately. There has been a lot of work, for example, on the Spark streaming side, on how to handle the multiple message delivery from Kafka, but you would much rather more than once than not at all.
How many days worth of data do you keep then, like a year?
Currently, I believe we're close to 18 months of data, and it's honestly, it's limited by the size of your cluster. So it's all commodity hardware with normal enterprise disks, and HDFS kind of gives you that layer to just use as much disk space as you have.
I was wondering which SIEMs you were comparing to your Kafka solution in your test results there.
Unfortunately, I cannot share which SIEM the client that we were benchmarking against was using. I can tell you it's a top 5 SIEM in the marketplace, but I can't go further than that.
So sorry, just on that, would you expect to see different results if you compared with more SIEMs? You mentioned you just use one.
Yeah, so depending on the SIEM, I imagine there would be different results. Unfortunately, that was the client that we were working with, so those are the results that I have. But the point that I was trying to make is any Fortune 500, if you can give them that level of performance to ask questions on their data, will gladly spend $50,000 to get that.
So you priced out the cost of the hardware, but
yes.
Did you include the cost of the expertise required to run that as opposed to running the SIEM? And just wondering, you know, it looks like it could scale, but you know, what about that other cost?
So that is not accounted in. I tried to just price it based on hardware and software licensing. Since they're all open source software, there is no software licensing. But yes, there is some expertise that goes in. There are companies such as like Cloudera, Hortonworks, MapR that give you a very, very easy interface to kind of just get up and running very quickly with a stack similar to this, that you could put, I would say, a basic security analyst, and it's a very followable tutorial to set it up.
Anybody else? All right, give me a round of applause.